And good evening, everyone. Thank you for the opportunity to speak at this conference today. We would like to tell you about the journey we have been on in Unilever R&D to digitally transform the way we do research and innovate using the power of data computing and advanced analytics. I'm Dr. Kumar Subramanyan and will be sharing with you some of the foundational layers we have put in place to drive agility and innovation in Unilever R&D. My colleague Andy White will then take you through a specific example on how we are applying some of these principles and tools in the domain of safety science in the context of our product innovations. I want to start by sharing with you the vision we have at Unilever R&D and how it underpins our innovation strategy. At the heart is our vision to innovate boldly for people and planet, which means we are very focused on delivering consumer-centric innovations, that is for the people, and those innovations need to be sustainable across its entire life cycle, from sourcing, manufacturing, distribution, consumer use, and disposal. And that is for the planet. Now, we are striving to achieve this by using data and analytics across the entire innovation process, starting from understanding and identifying consumer needs and product opportunities, leading to in silico product design and optimization through the efficient use of data, models, simulations, and through to efficient and sustainable manufacturing. And together, we believe that we can land powerful innovations faster in the marketplace. Now, our journey to becoming a world-class R&D focuses us on four critical dimensions of digital. The first pillar is data. Capture and managing high-quality data for use in R&D and beyond. The use of analytics and models and simulations, which codify the science and the knowledge we have to drive impactful discovery at speed. We are also implementing automation at scale, which involves developing the lab of the future by standardizing and automating experimental procedures for data capture, data generation, data storage, and even for modeling and analytics. And last but not the least is upskilling of the talent, driving future fit skills across R&D by connecting to a broader digital upskilling program that exists within the organization is a key part of delivering this capability within R&D. Now, by unleashing the power of digital in R&D, we have been able to make an impact on the speed of innovation by our ability to react very quickly to unexpected market changes, such as strengthening our supply chain resilience by finding alternatives to sunflower oil, for example, in our nutrition business, effectively addressing raw material price inflation and reducing the cost of our formulations without impacting performance in our home care business. On the efficiency pillar, automation allows for many repetitive and time-consuming tasks to be done quickly, freeing up time and resources for more value-adding activities. Digital technology allows better management and analysis of data, allowing business to make more informed decisions and identify areas of improvement. In the discovery pillar, we are able to enable scientists to process, analyze, and visualize large amounts of data in ways that were not possible before. Digital tools allow researchers to collect vast amounts of data from various sources, including experiments, simulations, and real-world observations. And with advanced algorithms and data analytics that include machine learning and AI methods, researchers can process and analyze the data to identify patterns, relationships, and trends that are difficult or impossible to detect using current methods. Digital tools also enable researchers to simulate and model complex systems such as biological processes, climate dynamics, chemical reactions without the need for physical experimentation. And this allows scientists to test hypotheses, generate predictions, and refine their understanding of the underlying mechanisms driving these systems. This is strongly underpinned by a data strategy that carefully examines all aspects of the data lifecycle, starting from data capture, data storage, access, and value creation, through a critical lens that ensures the principle of one source of the truth, while embedding high standards of data quality across the entire data lifecycle. In order to operationalize this, we use several state-of-the-art tools and platforms such as LIMS, ELN, Omics Data Manager, to cite a few examples of how we manage scientific experimental data. We also use solutions and platforms such as SAP PLM, Microsoft Azure, Siemens Teamcenter to capture and manage product-level data. Over to Andy now, who will talk in more detail as to how we are applying these principles and tools to accelerate our approaches in safety science.
Thanks, Kumar. As Kumar said, I sit within the Safety and Environmental Assurance Centre in Unilever, and I want to use the remaining time in this presentation to expand on his points around digital transformation and data strategy through the changing landscape and requirements we are experiencing in safety science and how we are starting to implement this. This slide just highlights the external challenges and drivers we are experiencing as a cosmetics and FMCG company. On the one hand, we were and still are in a changing regulatory landscape with a ban on animal testing for cosmetics that was implemented in 2013 in Europe, but it seems to be is extending to other countries. And aligned to that is a significant consumer preference for safe and sustainable products with no animal testing. We're aided by an external audit trail we're developing to build consumer trust. Between these two drivers was the ongoing science to develop and build the tools that could deliver this, and the need to ensure that they are both robust and scientifically credible. While some developing decision frameworks have emerged, it was clear that one of the things we're seeing is a large increase in data integration, more variability in the data types that wouldn't necessarily remain consistent, and larger volumes of data used at different stages in the decision making. And we needed to shift our systems in order to meet these new requirements. Also internally, we are seeing a list of growing requirements from a range of different end users. In order to simplify our process, we started looking at these through defining different personas and grouping these together, where we could start to see what the overall requirements were that were needed. Some of them consisted around the better need to find data and access quicker, wanting less friction and overhead in the systems that we have, but others were more focused, and we could see this balancing act emerging on how to drive more flexibility and capability for analysis to enable innovation in the analysis and the tool development that was going on, versus at the other end, improvements around the scale, more automation on standard processes alongside structure and governance to ensure that the right models and versions of those models could be combined with trusted data and documented to support the business decisions. Also for the developing NGRA space, while no standard approach had emerged, we started to focus on the principles that were either available either from the guidance bodies in terms of their expectations around transparency and reporting, alongside best practice that was available in the public domain, such as the FAIR guidelines or reproducible bioinformatics. This schematic really highlights how we started to build out the integrated platform. It started from building out a scalable and flexible data science environment from a broad search engine, workspaces, both collaborative and personal for code development, and links to code repositories, further access to larger scale of compute and workflow managers are also there and are aligned to deploy web-based tools to democratize the developed models. Alongside this has been the integration of a range of different data sources that meet the different proposed needs. It was clear that this was necessary, rather than trying to use a single data model to cover the range of different scenarios. For example, some are external data sources, through to managed but self-serve file stores to handle different data types, and then more structured curated data sources for more common data types, or where GLP requirements necessitate a LIMS environment, and then finally onto constrained R&D sources. These tend to be a mixture of internal and external builds, third-party services, with a requirement where we use them where requirements can be met and avoid reinventing something that's already there. Key to this success has been the integration of these within the data lab environment, both computational access and a GUI interface to cover consumer uses. Two other points on this slide. Those different personas have different entry points built on top to provide different and relevant experiences according to the need. For example, the business consumer can come in from the claim support system and use this in a guided process to call functions that directly call data from a subset of the data sources to provide an output and decision in a constrained manner, well governed, or without having to access the underlying data directly, such as addressing the questions around the biodegradability of substances. Whereas the data scientist or technical expert may come in via the search or the data modeling environment, either for data exploration and development or to pull on different data sources or use web-based tools that are also underpinned by the same functions as the business user, but with more flexibility in data applied or the parameters that are available to change. Secondly, in both the data modeling scope, we strive for that balance between self-service, high flexibility innovation and for early stage development, but also then increasing the governance process around the scientific evaluation and credibility and automation, and checks up both on the data and the tools as they become more prevalent. And we split between what we would call a research published model through to an industrialized model, and that depends both on A, the level of data governance, B, the decision consequence for what we're trying to do in terms of the data and the model, and the level of usage that's going to be present within it. Finally, I realised that time was starting to run out, and I wanted to highlight another couple of points around the data models. The aim has been to drive change and build data models that reduce the friction for people onboarding data, who might not necessarily always see the value in the extra effort in recording the additional metadata we request. So we try and make that as easy as possible to help people follow best practice. Also, we want them to take ownership of the new data types. So in the flexible environment, we provide minimal baseline templates that make it quick and simple and drive consistency with version control, while then also providing more defined templates that extend this and aid the data loader, the data owner, by incorporating ontology-driven auto-completes, visual metrics around completion levels achieved for quality, and differing levels of access with the ability to combine data files into data sets. However, this value also comes as we move from the data owner seeing how the data models align to ongoing regulatory and common standards, and this aids compliance. And here I highlight the current published OECD suggested data structure for omics type data, moving from study to experimental report to technical type, and finally to data analysis. And in this case, we're able to make the links from this directly to the data model used in Genestack, which is what we're using to support our requirements. And then again, a few key points around the data flow and integration of the systems. We have different use cases, but different routes for onboarding. So for example, you have a small user-driven app for bespoke data collection, versus when we have larger data sets, we have automated pipelines using Airflow to handle these larger data sets and ensuring the integrity of the data transfer against the metadata. This ensures trust and data credibility while not preventing anyone utilising the system. Once built, we can then implement more robust pipelines that run from data lab to drive consistency in the analysis and repeatability, utilising and pulling the right subsets of the raw data from the data source, ensuring that the files that are generated are extended and pushed back out to the data store, and version linked with the outputs, so that the outputs from this are linked to the initial inputs. In this case, this also includes incorporating the pipeline run IDs to ensure that we have the provenance of the data trail on what was done and when it was done. And finally, then we can build a GUI tool that sits over the top to extend usage of this beyond the data scientists back into the research scientists. Okay, I'm out of time. I just want to make a couple of quick points before finishing. Hopefully I've shown that we understood what the business challenges were we were facing and how we have tried to build the system to meet those business challenges, and we evaluate against those on a regular basis. Secondly, we've spent a lot of time trying to understand our end users. We've had previous systems which have failed because they've become too complex, and what that means is that for those people who are not using it on a daily basis, they soon lose the will to actually try and use it and understand and retrain on it. So trying to make it as intuitive as possible about what people are doing. And thirdly, use of early adopters who have acted as for us as key champions and super users, giving us early feedback on what it is. And then that builds a kind of a common goal, a stake in this, and that has helped us to build and give outreach to others. The final point is to acknowledge all of the help and effort that's gone into building this. So this is internally across many of our business functions and groups, the digital team, the IT teams, the foods, business, personal care categories, as well as SEAC, and also with our external collaborators. This has not just been an internal build. Capgemini, Genestack, Artians, Pega, and many more that have also helped us along this route. Thank you for your time.
Icon in your camera. Here it comes.
Craig, yeah, I can hear you.
We can. Can you put him on the screen? Great. Any questions? I know it's late in the day. I'm not seeing any questions from the audience, but we thank you very much, Andy, for coming on. And I don't know if you had any final comments or anything on your side.
No, well, one final comment. I think listen to some of the earlier speakers. Again, I want to highlight this product centric, and I think this is what we were trying to do was drive product centric approaches, understanding where the capability is going to be. Is it going to be a quick look at the data, see what sticks, and then how to use that? Or is this something that's going to be run out over to about 2,000 people? And therefore, what needs to be built to ensure that? And I think that's what we were trying to aim for in terms of flexibility. And we're not a massive group, but one of the things that we were looking at while doing that is how do we stop ourselves being spread too thin? And one of the ways was doing that was working out where external services align to what we need to do, and therefore what do we just need to build internally to actually also extend that. So it was a combination of internal build and external services that help us to get as far as we've got. And I think that's very important, that we don't try and build everything again ourselves, but we reuse what's available already out there.
Great, thank you. Any other final comments on any questions on the side? All right, let's thank Andy. Thank you so much, appreciate it.